well, thank you all. It's been a while. I think the last meetup was last year, I think, the San Francisco one. So I bugged Bryan like a lot for him to like organize this, because yeah, so Bryan Pardo, who's like I guess you're gonna introduce yourself later. I don't know how to do that, but or should I introduce you? I forgot. But anyway, so Bryan Pardo is a professor at Northwestern University. He's the head of the Interactive Audio Lab, and all of his children are like now here, like all the students are working. When I say here, I mean in the San Francisco Bay Area, I believe, right, for all of them, in fact. So I thought it would be a nice thing for Bryan to be basically the host, and the Interactive Audio Lab to be the host for this time. So let me just show like some introductory slides, and then we can start the presentation. So for those who do not know what is BISH Bash, so it's an informal networking meetup that we've been having for a few years now. It used to be hosted by technology companies and institutions in the San Francisco Bay Area. That was before the pandemic. And once we had the pandemic happening, we started doing this online. You can see on the screen like a bunch of companies and institutions which hosted this event in the past. So in the past, it was very nice. The company will host the event. We'll have free pizza, free beer, and then we can all meet in person. Well, we don't have the pizza and the beer anymore, but at least people from far away can join the meetup. Next, so what's the point of the BISH Bash? So basically, it's as I said, it's an informal networking meetup. The point is to just learn about the latest advances in the audio field and the related field. Meet some other people or the bright mind, share some of your knowledge, learn new things, and have some fun. I mean, the whole point, the main point is to do some networking. So yeah, please keep the momentum going. I know it's been a while and we've been trying to have new hosts, but the pandemic didn't help. So spread the word. If you want to organize the next BISH Bash, it's very simple. There's not much to do. Just have some presentation, and we can have like a Zoom meeting like this one. So it's quite simple. And I have some link over there. So if you you have the meetup link. You can also see the videos on the YouTube channel. Just search for BISH Bash Meetup. The video for this presentation will be online. And just another thing, we have a bunch of these BISH Bash around the world. This one is in San Francisco. We have a few meetups since 2013. This is the 4th virtual meetup. Tokyo BISH Bash has been doing very well, also 5 virtual meetups since 2020. London BISH Bash is doing well too. They had a recent virtual meetup. Paris BISH Bash is going to have 1 physical meetup now that France is kind of open. And we have a newcomer, which is the Latin America BISH Bash, where they had 1 virtual BISH Bash already, but they're going to have 1 more next week. So if you guys want to join, please do. And let's see what's happening in Latin America. Future BISH Bash, I hope this kind of BISH Bash can happen elsewhere in the world, especially in underrepresented region like Southeast Asia, China, or India. So I'm talking to some friends and see if we can make this happen. I guess that's it. So now, again, let me reintroduce Professor Bryan Pardo from Northwestern University, head of the Interactive Audio Lab, who used to be my supervisor, and I'm happy to have him host this BISH Bash. Okay, you go ahead, Bryan.
Okay, thank you for that introduction, Zafar. As Zafar mentioned, I'm a professor at Northwestern University, and we have the Interactive Audio Lab. We're going to have 4 great talks for you today from 4 wonderful researchers. The first one's going to be Max Morrison on neural pitch shifting and time stretching. Then Patrick O'Reilly is going to talk about adversarial attacks on voice recognition. Hugo Flores Garcia is going to talk to you about how you can add your deep learning models to Audacity. So at last, you can directly have users use your stuff. Ethan Manilow is going to show you how you can take existing pre-trained models used for something else entirely, and without any retraining, use them for source separation, which is exciting. Every one of these talks is going to be 15 minutes with 5 minutes for questions. I'll ask you to hold up, like maybe keep yourself muted during the talk. If you want to ask a question, maybe do it in the chat. And then at the end of the 15 minutes, we'll have 5 minutes there. And after all of the talks, we're going to have a brief sort of shout out session where people, like, let's say your name is Jonathan LaRue and you want to get interns for Merle. That would be a great moment for you to let people know you're looking. And then once we've done that, hey, Jonathan, once we've done that, we're going to have breakout sessions. And so each one of the speakers is going to be in one of the 4 breakout rooms, and the number of the breakout room will correspond to their order. So, breakout room 1 will have Max Morrison, breakout room 2, Patrick O'Reilly, like that. And then you can go and have more in-depth conversations with each other or with the speakers. And for those of you who just want to hang out, just stay in the main room and you can chat with me or whoever is hanging out in the main room. And so that's going to be the overall format for it. And we're right on time. So I'm just going to now send it on over to Max Morrison, who's going to be our first speaker. So Max, why don't you take it away?
Hi, everyone. Are you able to see my screen?
Yep. Yes.
Yes.
All right. Hi, everyone. My name is Max. I'm a 4th-year PhD candidate working with Bryan. Today, I'll be telling you about my work, neural pitch shifting and time stretching with controllable LPCNet. This is a current submission to ICAST 2022 and is in collaboration with Adobe Research, specifically Zayu Jin, Nick Bryan, and Juan Pablo Caceres. So this work is about the pitch shifting and time stretching of clean, non-reverberant speech signals. And this is useful for audiovisual synchronization, such as syncing dialogue, singing voice editing like auto-tune, as well as prosody editing, so taking a speech recording and maybe changing where an emphasis lies or changing the excitement level of the speaker. Prior work for pitch shifting and time stretching of speech includes DSP-based methods like straight, world, or TDP solo, as well as neural methods such as USF-GAN, pitch shifting wavenet, and fast pitch, among others. Among all of those here that have been evaluated for pitch shifting quality or time stretching, TDP solo has the highest subjective quality. However, it's non-parametric. This is a slight disadvantage. It doesn't have a representation that can parameterize, that can be a target for like generation or speech coding. As well, these DSP-based methods are currently winning in terms of pitch accuracy when doing pitch shifting. And these neural methods have improved substantially over the last couple of years. I have no doubt that they will outperform and continue to improve, outperform DSP-based methods and continue to improve over the next couple of years. However, all the current methods have some sort of drawback. For instance, USF-GAN has subjective quality that's about on par with World, not quite TDP solo. Pitch shifting wavenet is a little better than World, but not quite as good as TDP solo. It's also slow and it's single speaker. It only works for 1 speaker at a time. And then fast pitch also only works for 1 speaker at a time, requires 2 networks, ends up changing the timbre by regenerating the spectral features. So really what we want something that has subjective quality at least as good as TDP solo. We want it to be fast. We want it to work for any speaker. As well, we wanted to have good enough accuracy for whatever application domain that we're working in. For instance, for prosody editing, for English prosody, humans tend to not discern differences less than 150 cents in pitch. So that would be a reasonable threshold to look at. So to this end, we're going to use LPCNet to create this new pitch shifter and time stretcher. LPCNet is this autoregressive neural vocoder. It works in real time, so it's fast enough for our use case. It also works out of the box with support for multiple speakers. The inputs to LPCNet include the pitch, periodicity, and BFCC or Bark scale cepstral coefficient features. These are similar to like Mel scale cepstral coefficients. It's just changing the location of the frequency, the center frequency of the triangular filters. So the core idea with LPCNet, the reason why we use it is because it has this nice inductive bias for learning pitch. Specifically, it's this source filter model. And source filter models of speech will break down the speech into basically the source, which is modeling the vibration of the glottis in the throat, and a filter which models the shape of the mouth and how that shapes the signal coming from the glottis. So the LPCNet is a source filter model. It uses a neural network to predict the source. They call it the excitation, and they do this autoregressively, one sample at a time. Because the glottis is where all the pitch information is contained, including not just what the pitch is, but to what extent it is pitched. So for instance, if you have a sound like sh, it's an unpitched sound or unvoiced sound. All of that is present in the excitation or source. So LPCNet is honing in on just the specific components of speech responsible for the pitch. So we're going to do pitch shifting and time stretching. For time stretching, this has already been done by the original authors. It was done on companion websites, the original paper, where they show that you can vary the relative rates of these two networks in LPCNet, the frame rate and sample rate network, and you can get pitch shifting. So for example, let's take this original audio that we'll edit.
I've been in 2 finals and I've got a medal.
First, we're just going to do reconstruction. So we're going to compute the input features, pass them through the network. We'll get the reconstructed waveform out.
I've been in 2 finals and I've got a medal.
So when we're doing that, we're sampling about 160 times for every frame. So we have a hop size of 160. Now let's double that. We'll sample 320 times per frame.
I've been in 2 finals and I've got a medal.
And next we'll half that and just do 80 times per frame.
I've been in 2 finals and I've got a medal.
So we see that LPCNet out of the box is pretty good with time stretching. However, its pitch shifting performance leaves something to be desired. So let's do the same thing. Let's try to take some original speech and edit it. So here's the original speech.
And the shorebirds were fishing and crying all around us.
And so that's this black line here. Let's try to move it down to this blue line, which is 2/3 of the original speech. So first using TDP Sola, the DSP-based line.
And the shorebirds were fishing and crying all around us.
Next, let's try using LPCNet so we had these 3 features that go into LPCNet, the pitch, periodicity, and BFCCs. The pitch, we're going to just take it, instead of giving the original pitch in, we'll give the blue line the shifted pitch.
And the shorebirds were fishing and crying all around us.
And we see that it's not actually a higher pitch. It's that there's no pitch at all. It's completely aperiodic. It's noisy audio. The network has failed to generate something that has a pitch. And we're using the voice-on-voice tokens from the original, which is why it's all the way up here. So what's happening here is that the pitch and the BFCCs both contain some information about the pitch. And the network, when you change just the pitch, but don't change the BFCCs, the network freaks out. It doesn't know what to do when these things are mismatched. So what we need to do is find some sort of technique to allow the network to be okay with that mismatch. And when we do that with the methods that we will describe shortly, we'll get something that sounds like this.
And the shorebirds were fishing and crying all around us.
So relative to LPCNet, controllable LPCNet or CLPCNet, it's going to do 2 things. One is going to work on the pitch representation, both the quantization and estimation steps, as well as it'll work on the data augmentation. And again, our goal here is try to decorrelate the pitch from the BFCC features such that the pitch can be independently maneuvered. As well, one nice thing we'll look at is trying to pitch shift to extreme frequencies, very low frequencies, very high frequencies. So first we'll look at the pitch quantization. This is the pitch quantization of LPCNet. So for instance, this is 128 hertz here, so 2 to the power 7, 2 to the power 8, 256 hertz here. And we see a couple of issues with this quantization. One is we can't represent very low male voices. As well, we are using too much capacity for representation of very low frequencies that are not often seen. And then our bin spacing up at higher frequencies is greater than the just noticeable difference JND of human pitch perception, about 20 hertz. So we're going to lose some accuracy here. And then we're also representing frequencies beyond those that are produced in human speech. So we can swap all this out for a simple perceptually linear quantization of the pitch range from about 50 to 550 hertz. The resulting bins have a width of about 16 cents per bin, making it within the JND. So what we find to be even more crucial, so again, we're trying to decorrelate the pitch so that it can be independently maneuvered. Well, the network is going to look at the BFCCs for pitch when the pitch feature is inaccurate. So we find it really important to get the pitch estimation as accurate as possible. And by that, we mean both the pitch and periodicity. Periodicity is a relaxation of the voiced unvoiced. So if unvoiced is 0, voiced is 1. This is some value between 0 and 1 that says to what extent is the glottis vibrating periodically. LPCNet uses yin by default. And we can see that there's a couple that this representation has this very coarse temporal resolution. And if there's pitch error when the periodicity is low, that's not a problem. Because if the periodicity is low, that's saying like this is white noise, this is some noisy signal. It does not have a pitch defined. However, if the periodicity is high and there is pitch error, then the network is being told there should be a pitch here. It's being told what the pitch is. However, that is very far off from what the pitch actually is. And it then looks at the BFCCs, which has slightly better pitch resolution than what it's getting from the pitch. So let's listen just to verify that this is an issue. Listen for the word there, and at the end of the word there, you can verify that it does not have this upward shift.
From there, they can go anywhere.
So we found that changing the pitch estimation, changing the pitch representation really helps to improve the pitch shifting performance and the pitch accuracy. Next, we're going to look at a resampling augmentation that'll A, do the same thing, then B also allows us to shift to very low and very high frequencies, a wider range than we'd usually be able to. So neural pitch shifters tend to be constrained to the distribution of pitch that they were trained on. So for instance, with VCTK, you see like male and female pitch distributions here. And this was our training set before augmentation. After our augmentation, we want to get something that's a little more uniform over the range of 50 to 550 hertz to allow for pitch shifting over this entire range. So this resampling we're going to do, it's very simple. We're going to take a speech file, we're going to resample it from some other sampling rate that it is not to its current sampling rate. And what that'll do, it'll change the duration, it'll change the pitch, and also change the performance. So it's going to sound a little weird. Let's listen to what it sounds like.
It's a technical demand.
That's the original before augmentation. Here's shifting down with this augmentation.
It's a technical demand.
And then shifting upwards.
It's a technical demand.
And clearly, we don't want our networks to actually generate something that sounds like this. It sounds very, very comical. However, the representation of performance is isolated within the BFCCs. And when you're pitch shifting, when you're actually using CLPCNet, the BFCCs are coming from the original audio. So if your original audio doesn't have these artifacts, your output won't have these artifacts. So this is really nice. We just got a much larger clean speech data set. Has a nice pitch distribution that allows us to shift to a wider range. It also is, I think, a little bit of a speaker augmentation where we're changing the performance and it gives you a slightly different sounding speaker. Yeah, so this really helps us to be able to improve the pitch shifting performance as well as shift to a wider range of frequencies. Now for evaluation, we're going to evaluate both the objective and subjective performance on constant and variable ratio pitch shifting and time stretching. For baselines, we'll use LPCNets as well as World and TDP Solar, the DSP-based baselines. And for datasets, we'll use VCTK for training as well as DAPS and RAVDES for evaluation. Our metrics that we'll use for pitch shifting, first we'll use F1. So if you remember that periodicity, we can threshold that periodicity at some point, where below it, it's unvoiced, above it, it's voiced. We can do that for both the generated and ground truth audio, and we can compute the frame-wise binary classification decision of the voice on voice. We're gonna get the F1 score of that. And then for frames where both the generated and ground truth are voiced, we are going to get the average error of the pitch in cents. It's important that both regions be voiced. If any of them is unvoiced, then the magnitude of the pitch error can be arbitrarily large. It can be undefined. So we're going to listen to a little bit more. So first we'll listen to some constant ratio pitch shifting. Here's some original audio for us to edit.
The Hispaniola was rolling scuppers under in the ocean swell.
We'll start by shifting down with a ratio of 4/5. First, you'll hear the TDP Sola, the DSP-based baseline.
The Hispaniola was rolling scuppers under in the ocean swell.
Next is LPCNet, the baseline.
The Hispaniola was rolling scuppers under in the ocean swell.
And lastly, our proposed CLPCNet.
The Hispaniola was rolling scuppers under in the ocean swell.
Now let's go up. We'll do the reciprocal ratio of 5/4. First with TDP Sola.
The Hispaniola was rolling scuppers under in the ocean swell.
Next with LPCNet, the baseline.
The Hispaniola was rolling scuppers under in the ocean swell.
And you may have heard an artifact that got much quieter. That is just an artifact that is induced by the network. And then lastly, CLPCNet, our proposed method.
The Hispaniola was rolling scuppers under in the ocean swell.
Looking at the subjective performance of pitch shifting at these various ratios, if we look at the purple lines, we see they're always greater than the red lines. So CLPCNet always outperforms LPCNet. We see the same thing with World, except for at a pitch shifting ratio of 1.5. That's one place where World outperforms our method. But we outperform World on all other conditions here. And then for TDP Sola, we tie everywhere here except for a pitch shifting ratio of 1.5, where TDP Sola does win. So for time stretching, CLPCNet again beats LPCNet everywhere. For Worlds, it beats it everywhere below 1.0 and then ties for 1.0 or greater. And then for TDP Sola, it ties everywhere except 0.71 and then 1.0, which is really a no-op for a time stretch. So we have that we're definitely beating World with only one condition where World beats us. So we do have a new best parametric method for pitch shifting time stretching. We still haven't quite beaten TDP Sola. So let's see if we can find something where CLPCNet really is the state of the art. And that's going to be prosody editing or variable ratio pitch shifting and time stretching. So what we're going to do, we're going to take one speaker saying one thing in two different ways. And we're going to use pitch shifting and time stretching to make the first way sound like the second way. So here's the first way.
Kids are talking by the door.
Here's the second way.
Kids are talking by the door.
First, let's use TDP solo, the DSP-based baseline.
Kids are talking by the door.
Now we'll try to use LPCNet.
Kids are talking by the door.
And lastly, I proposed CLPCNet.
Kids are talking by the door.
Looking at the objective results, we see that CLPCNet isn't quite as accurate as TDP solo or WILD yet, like other neural baselines right now. It's just a little bit lower in terms of F1, it's almost there. And then RMS is a little bit more of a gap, but it's significantly better than LPCNets. And a lot of the noisiness that you hear in LPCNets, you really see show up in this F1 score here. Looking at subjective results, CLPCNet is significantly preferred over all other methods, making it the state of the art in terms of subjective performance for prosody editing. So in conclusion, CLPCNet fixes some inaccuracies of LPCNet via a new pitch representation, as well as a data augmentation step. It is the first neural method to outperform DSP-based methods for pitch shifting and time stretching on subjective quality, and specifically subjective quality of prosody editing, where it is a new state of the art. The code, paper, and listening examples are all available from the URL that you see on your screen. The code will be released within this week. Thank you for listening, and I'll be happy to answer a couple minutes of questions.
All right, the floor is open. Does anyone want to ask a question about prosody editing with a neural vocoder?
Yeah, could I ask a quick question?
Please.
Thanks, Max. That was a cool presentation. I'm just curious, like, it seems like a kind of a rare task where the DSP methods still seem to be, you know, kind of winning in some, at least in some cases. So I'm curious, like, would it be possible to potentially start with TDP Sola and, you know, build a model around that can kind of take advantage of that inductive bias and just like that's the fallback plan? Like, it's never going to do worse than that?
Yeah, I think there's something to be said for the inductive bias of DSP-based methods for pitch-related tasks being really hard to replicate with neural networks. So that makes a lot of sense to me, trying to start with TDP Sola, as long as you don't mind having no parametric representation, which I think for this task, that's totally fine, or for prosody editing. Yeah, something like trying to approach this from the ground up on a DSP-based method, I'd be very interested in.
Nice. And another quick question I had was just curious if this works at all for singing voice. If you tried it?
I've not tried it as much for singing voice. You'd have a little bit of trouble with the RMS. Mm-hmm. So I think the RMS is such that it's still going to be a little bit inaccurate for musical applications if you want to be really, really in tune. Whereas we have a little bit of leeway when we're doing prosody editing.
Gotcha. Cool. Thanks.
Yeah.
I'm sorry, I joined a little bit late. So you mentioned the lip movement. So I didn't understand that. Did you use any visual information?
Lip movement. Do you remember where I was talking about lip movement?
I think it was when you were talking about the adaptive biases.
Yeah. Oh, the source filter model, right? Yeah, no, not the lip movement. So it's a source filter model, and it's just a model. It's not actually using like a biological mechanism, just a sort of coarse approximation of it.
I see. Thank you.
But it models speech as a source and a filter, where like the source is like this vibration that happens in the throat, and then sort of how you can like change your mouth and change vowel shape, like ow, wow, wow, while keeping the source the same. It's basically just separating those two things.
Excuse me, I have a question. So for the LPCNet, when you build it up, is it like the original LPCNet structure? Did you like make any modification on that?
Right, so there are no changes related to the architecture. The closest change to the architecture is the quantization, but that's really a pre-processing step. Mm-hmm. So the architecture itself is identical, which is also nice. We haven't ported it for being real-time just yet. but it should be plug and play with original code because the model has the same architecture.
I see. Because actually, I noticed that in your demo, there's still some like artifacts, some like noisy from the LPCNet. I remember actually previously, it seemed like Microsoft or yeah, Microsoft actually proposed a modified LPCNet. My fix the issues for you. They have actually they have like better performance on the TTS topic over the original LPCNet. Maybe you can check that.
Yeah, sounds good. I'll take a look.
Okay, well, to keep us on time, we're going to need to move on to the next speaker. If you would like to unmic for a moment to give Max a round of applause, that would be awesome. Can you give him a little?
Nice code on LPC.net.
All right, so who do we have next? I believe it's Patrick O'Reilly, yes? So Patrick, why don't you, so he was talking about how to make a speech better in some sense. What do you, tell us what you're here to talk about.
We're making evil speech. I'm going to be talking about adversarial examples as soon as I figure out how to share my screen. 1 second.
Patrick is probably the only one who has a Halloween themed research.
Exactly. Yeah, it's all about disguise. So really quick, let me just check my sound. Great. So hopefully you see the screen here. Hopefully that's coming through. Could somebody just shout out really quick?
Yes, it's coming through.
Great. Okay. Awesome. Okay. So I'm Patrick O'Reilly. I am a second-year PhD student working with Bryan. And today I'm going to be talking about adversarial attacks in the audio domain with a focus on a novel attack algorithm. And this work is also submitted to ICAST 2022. Great. So these days, it's increasingly common to interact with products through voice interfaces. We can direct queries or commands to voice assistants like Siri or Alexa, and we can even verify our identity via voice print technology in sensitive applications like mobile banking. So by and large, voice interfaces rely on neural networks to accomplish tasks, things like speech recognition or speaker verification. And as we saw with the spread of neural network-based computer vision systems a little while ago, it's possible to fool neural networks by carefully crafting malicious inputs. And we call these inputs adversarial examples. In computer vision, we can think of them as images that look very much like one thing to a human, but have been perturbed maliciously to look like something completely different to a neural network model. And here we can see that the image on the left has actually been altered imperceptibly by adding a small, carefully crafted perturbation pixel by pixel to cause the network to make an incorrect prediction, in this case, given rather than panda. Obviously, if a malicious actor can make a commercial neural network think that it's seeing something when it is definitely not seeing that, right? It's seeing something completely different to what a human observer would judge. That's a bad thing. And this has motivated a great deal of research over the past 7 or so years into crafting both new attacks and defenses, with the goal of understanding how to make systems more robust. So we might consider whether neural network-based voice interfaces also share this vulnerability. And the short answer is that yes, we can perturb a digital representation of an audio waveform just as we would an image to craft an audio adversarial example in this case. Thus, we can craft audio that sounds benign to humans, but that can carry hidden malicious content when parsed by a voice interface. And some of the concerns here are at times a little bit overblown in this research area in general. So with well-engineered systems, really, they're not going to endanger users, hopefully, due to a simple voice command, right? There's no way to surreptitiously trigger an ejector seat in a Tesla just by playing adversarial music over the radio. But these attacks do potentially pose risks for certain real-world applications like voice print authentication. So let's assume that we have a voice interface and it's designed to verify a speaker's identity. And we're some malicious actor trying to modify an audio input to the system. So in this case, that the system thinks that we are Bob. It thinks that it's hearing audio that's an utterance from this speaker Bob. So depending on our level of knowledge of the system, we can either construct an exact replica of the underlying neural network system or a rough approximation. And we can construct a loss function that's minimized when the input audio to the system is identified as this network by Bob. We can then perform iterative gradient-based optimization on the input directly rather than the parameters of the model as we're kind of used to in machine learning. And that's because this network is going to be fully differentiable. And we can do this until our input speaker is misclassified by the network as Bob. And ideally, our final adversarial input, once we're done optimizing, it sounds identical or similar to our starting input. That is, the perturbation that we've added to this audio waveform is going to be small enough as to be inconspicuous. And if we have to add, you can think about this as kind of a thought experiment, right? If we have to add deafeningly loud noise to our input to fool the network, we're not really fooling it in the sense that you could argue the ground truth has changed, or at the very least, your attack is going to be extremely conspicuous and probably get spotted. Okay, and one more thing actually I'd like to really quickly note is that not just any noisy perturbation will do. We're carefully optimizing over potentially a large number of iterations to find an exact perturbation that's going to fool this network. And so then that raises the potential for these perturbations to be brittle in practice, because any small change to this perturbation might render it ineffective when it's actually passed to the network. So the main thrust of the work I'll be presenting today, let me get right down to business. Let's assume that we have a very simplified scenario in which we want to play speech from one person to a speaker verification system and convince this system that the speech is coming from another specific person that we choose. Essentially, we're spoofing the identity of this target speaker. So we can say that we're starting with a recording of Alice.
And the wan oracle, having spoken, she sat down.
We want to convince the system that this is actually an utterance coming from Bob.
Uncas cast his skin and stepped forth in his own beautiful proportions.
Okay. And let's also say for now that we want this attack to work when it's played in the real world, and we'll elaborate a little bit on what this means. So verification models are generally pretty good. In the real world experiments that we ran actually on this particular pair of audio files, this recording of Alice was never once misrecognized as Bob when we actually played this out in the real world. And so first we could try what I'm going to call a generic attack, where we follow that optimization procedure I discussed a couple of slides ago. And this approach is adapted roughly verbatim from the image domain, except we add noise sample by sample rather than pixel by pixel. The assumption is that adding a little bit of noise coordinate by coordinate will be imperceptible. And while this is true to some extent in the image domain, this actually does not align with human auditory perception at all. So thus, even if we follow best practices and try and pick our parameters as best we can, we're often going to end up with audibly distorted inputs. So here, if we take a listen to our starting audio of Alice.
And the wan oracle, having spoken.
And then we listen to what happens at the end of our attack when we're done optimizing.
And the wan oracle, having spoken, she sat down.
So I don't know how well the audio is coming through, but hopefully you hear some kind of background noise that almost sounds like a whisper. And I'll play that one more time.
And the wan oracle, having spoken, she sat down.
And depending on the system you're attacking and how difficult of a real world situation you're trying to make your attack successful in, that noise can be even more perceptible. So we might try and improve on this attack with a psychoacoustically motivated perceptual loss function and a more complicated multi-stage optimization procedure. We can think of this again as another flavor of the basic image domain attack. And generally, this is our best current method for making adversarial perturbations as imperceptible as possible. The downside with this compared to the generic method is that we can potentially incur extra complexity and computational expense. And this may or may not be a concern as an attacker, depending on what scenario you're operating in. So here is our new adversarial audio.
And the wan oracle, having spoken, she sat down.
And so again, this may not come through great over Zoom, but we've lost most of that whispery perturbation. And now we only have a little bit of white noise that we can be hearing. Okay. And so finally, what we propose is a novel attack algorithm based on a common audio transformation known as adaptive filtering. We were able to match or improve the perceptual quality of these frequency masking based attacks like those with Quinn et al. Without requiring a computationally expensive perceptual regularization method or a complex optimization procedure. And if you're having any difficulty hearing these audio differences, by the way, I'm going to have a link at the end of the presentation to a project page where you can go through and listen for yourself. So here's the filter attack.
And the wan oracle, having spoken, she sat down.
Here's that masking attack again.
And the wan oracle, having spoken, she sat down.
So this difference can be hard to spot over Zoom, but I think at the very least, I hope that you're convinced that this is not going to be more perceptible than that frequency masking attack. Great. Okay. So rather than, So under these somewhat important, but also a little bit arbitrary criteria, we have the most check marks here. And so maybe I'll claim that we win, which is a bit of a simplification. But I want to spend some time now filling in the details on how we came up with this attack, what motivated this attack, and how it works under the hood. So rather than refine a noisy additive perturbation to the waveform, our proposed method optimizes a set of filter controls, allowing for simplified, interpretable control of our perturbations in the frequency domain without producing noisy artifacts. So why do we run into these noise issues? Why is the typical approach to do additive noise at the waveform? We're going to start delving into these details. But if you look back at the image domain example I showed with the panda, the key thing was that we could add a small amount of noise coordinate by coordinate and get away with imperceptibility. And that's not necessarily the case in the audio domain for a variety of reasons. And so we're trying to take an audio domain transformation here and apply that in an attack context. That's really the core of our approach. Great. And so I think the best way to get at some of these questions is just to hop right into the details of the attack. And so let's talk about how we might want to attack a voice interface. So we talked about this speaker verification task. We're going to confirm a speaker's claimed identity, typically by comparing new input utterances against an enrolled profile made from previous recorded utterances from that speaker. So we can grab a large and reasonably accurate model with good real world performance. Here's one, and this has been featured in a couple of other attack papers. And so this model is trained to map arbitrary length utterances to text independent discriminative embeddings, meaning that utterances from the same speaker should be clustered close together in the model's embedding space, and utterances from different speakers should be spaced fairly far away in the embedding space. And as with others who have attacked this in similar models, we're going to simplify this task to simply spoof an embedding of a single utterance in the embedding space. So if we want to impersonate Bob for now, we're going to assume it's enough to be able to take any recording from Alice and get it very close to an embedding of a known utterance from Bob we have access to. And how are we getting our audio to the model in practice? Well, in what you might call an over-the-line setting, we would assume we'd have direct digital access to this model, and we can just pass our attack to the model as digital audio. However, often an attacker will be operating what we might call an over-the-air setting, where the malicious audio has to actually be played through a speaker first and then received by a microphone before being passed to the victim model. And this is a more challenging and often realistic setting, depending on the problem. So that's what we're going to focus on. And all the attacks that I played you before, by the way, were crafted for this challenging over-the-air setting. And what I mean when I'm talking about a challenging over-the-air setting, I'll give a little example here, is let's assume that we start with this audio recording. It's not adversarial, this is just our starting audio.
And the wan oracle, having spoken, she sat down.
By the time that audio makes it into the victim model, after going through a speaker, an acoustic environment, and in through a microphone, it might sound something more like this.
And the wan oracle, having spoken, she sat.
And that's pretty worst case, but in general, we're going to be accounting for those kinds of acoustic distortions. So to craft adversarial examples that can withstand playback in the real world, we want to optimize using an end-to-end differentiable pipeline that mimics a practical over-the-air setting. For now, we're just going to focus on crafting adversarial speech recordings, but in general, we can craft all sorts of adversarial noises using this iterative optimization approach. And we can apply random simulated acoustic distortions to our adversarial audio as we optimize mimicking these real-world playback environments. We're also just going to apply basic pre-processing as well to mimic real-world systems. And we have our model which produces embeddings. Now note that we're actually optimizing two loss terms here. This L sub aux, our auxiliary loss, is there to encourage our perturbation to be as imperceptible as possible. And our L sub adv, our adversarial loss, is there to encourage our perturbation to fool the system in the way we want. In this case, to bring the embedding of our adversarial utterance as close as possible to the embedding of our target utterance. And this is potentially where we run into a problem, which is that in these challenging real-world over-the-air settings, as you optimize attacks to be successful under these kind of high magnitude acoustic distortions, there's a common phenomenon where you have to introduce larger and larger magnitude perturbations in order to ensure success. And with these waveform additive attacks, like the generic attack or even the Quinidal attack, that can manifest as audible noise artifacts. So here are some examples of existing attacks against various models where they kind of run into this problem when optimizing their attacks to work in the real world. This one is against a speech recognition model. So different attack algorithm and different model, but just for an idea of what these can sound like. Oh, oops. Let's get back to the audio.
Hold your nose to keep the smell from disabling your motor functions.
So that's your starting audio. And after your adversarial optimization, you might end up with something that sounds like this.
Hold your nose to keep the smells from disabling your motor functions.
Which is fairly conspicuous. Alternately, maybe you're attacking a speaker recognition model like we are, and you want to create something like an adversarial notification sound. So you might start with something like this. But then as you optimize, you start getting these noisy artifacts, which kind of sounds like running water in that one. I'll play that again. Okay. So rather than focus on maybe finding a better auxiliary loss, we can look at introducing adversarial perturbations through a different differentiable audio transformation that isn't biased towards noisy artifacts. And so adaptive filtering is one such transformation that dynamically shapes the frequency content of audio. And by crafting adversarial features directly in the frequency domain, we can avoid these noise-like artifacts associated with unstructured waveform perturbations. And this perceptual advantage comes basically for free with the change in approach. We don't need a complex perceptual regularization procedure because the filtering is itself the regularization procedure. So for a brief and simplified recap of filtering audio, let's say we start with this recording.
And the wan oracle, having spoken, she sat down.
So for example, we can suppress low frequency energy to end up with something that sounds thinner or tinnier.
And the wan oracle, having spoken, she sat down.
We can boost and attenuate in specific frequency ranges.
And the wan oracle, having spoken, she sat down.
And there's no reason we need to keep our filters fixed over time. We can allow them to change dynamically.
And the wan oracle, having spoken, she sat down.
So for a fixed segment of audio, we can specify a filter's response with a sparsely sampled frequency domain transfer function. Arbitrarily here, I've constructed one that's kind of attenuating the extreme low and high frequencies and boosting in the middle of the passband. Note that the frequency scaling here is linear. And to apply this filter to a segment of audio, we can actually roughly follow the approach that Engel et al. Used in their differentiable digital signal processing work. That's from Google Magenta. I'm going to skip over some of the fine-grained details in the interest of time. And so to make our filter adaptive, we can break up our audio into short segments and allow the filter's response to vary over these segments or frames, thereby shaping the frequency content dynamically. And so we can think of our transfer functions as being kind of a low-dimensional adversarial control signal, because we don't want just any filters, we want adversarial filter responses. So we can plug our adaptive filter into our adversarial optimization, and now we're tweaking filter parameters and controlling the filter with the input, rather than tweaking an additive perturbation to the input. Our auxiliary loss function becomes less important now because we can simply bound the filter parameters if we want to prevent extreme transformations. But in some tasks, we do find that a simple auxiliary loss can be helpful, something like a frame-wise MFCC distance or even a waveform L2 loss. And if we set a high enough frame length and use a low enough number of filter bands, our filter parameterization can actually be very, very low dimensional, especially when compared to something like an additive waveform perturbation. And again, we're going to optimize these filter parameters just as we would an additive perturbation. No complex multi-stage optimization procedure is required. So what are the benefits of this proposed filtering approach? So one, when we introduce perturbations at the filter representation rather than at the waveform, we avoid these noise-like artifacts in challenging over-the-air environments. And so here, we'll have our starting audio of Alice.
And the wan oracle, having spoken, she sat down.
And as kind of a recap, here's our generic attack.
And the wan oracle, having spoken, she sat down.
Here is that frequency masking attack.
And the wan oracle, having spoken, she sat down.
And here is our proposed adaptive filtering attack.
And the wan oracle, having spoken, she sat down.
Again, as we kind of crank up the difficulty of these acoustic distortions, and we're required to have hardier and more robust attacks, in typical attacks, you get more and more kind of a noisy audible perturbation. In the case of this frequency masking attack, you should be able to hear a little bit of additional noise.
And the wan oracle, having spoken, she sat down.
In this case, this attack isn't particularly egregious, and it may be hard to hear the difference over Zoom. Again, I'm going to encourage you guys to check out our audio examples. I'll provide the link at the end. With our adaptive filtering attack, though, we don't get any noisy artifacts as we crank the difficulty.
And the wan oracle, having spoken, she sat down.
Okay. And so what we do is we went ahead and we conducted a user study where we asked participants to, given a forced choice comparison between this state-of-the-art frequency masking attack and our adaptive filtering attack, and matching for attack effectiveness against our speaker verification model, we asked users to identify which audio sounded closest to the provided starting reference audio. And by a margin of roughly 2 to 1, over about 1,200 comparisons, listeners rated our attack audio as closest to the original audio, showing that our simple filtering approach can compete with a complex state-of-the-art frequency masking attack without all of the bells and whistles. And interestingly, this is despite the fact that our attack actually alters the audio waveform much more drastically, at least as measured by the infinity or 2 norms. We're altering the waveform by about 3 times as much as measured by either of these norms. Okay, and that's really the key. By applying a little domain knowledge and choosing a different representation at which to perform our attack, we're able to succeed with a much simpler method. Great. And so one thing I want to mention really briefly as I come to the end here is that I think this work kind of coincides with other recent works that have also started now to explore kind of audio specific transformations for crafting these adversarial perturbations. Things like looking specifically at generative models on spectral representations, or considering the phase, or even crafting adversarial music with things like heartless strong synthesis. So that's really neat. And we plan to explore kind of filter-based attacks against other systems, including more robust speaker verification pipelines that more closely mimic those used in production systems. And we also want to explore the implications of this for defending and building more robust models that can handle high magnitude frequency domain perturbations. Great. And so that's what I've got right now. The audio examples can be found at this link right here. And I don't know how much time we have questions, but I'll be around in the breakout session. So thank you very much.
Well, you actually ran right up to the edge. So I think we have time for maybe one question before we have to move on to the next speaker. So who here would like to ask that key crucial question?
There's one in the Zoom chat already.
Yeah.
Hey, quick question. Yeah, I'm wondering what you see the accuracy in voice print technologies being able to differentiate this for people who want to spoof voice prints. And shout out from the Google developer group in Silicon Valley.
Yeah. So getting, I guess, so one part of this going forward is definitely getting a more kind of robust and realistic picture of what it's like to attack a voice print system. There are a couple of really interesting recent papers, I want to say, from Cassis et al. Up at Waterloo, and also from Zhang et al., I think in last ICASP, that consider closer approximations of real world voice print systems. The important yet is that they're able to attack these systems fairly well, even when they implement simple defenses like replay detection or a speech verification check. So I don't know what we're looking for.
One of the things I think that's really interesting to look at is protecting against that, because we're seeing attacks with people with 3D printed masks for visual ones. Is one of the things we look at for audio, and I also do some interesting contract stuff and stuff for keeping the arsenal of democracy free in Silicon Valley. My family's done it for 10 generations, technology-wise, is you can tell with the voice if someone's under stressors. So that's why people in really high leverage situations, national security and others, and banks and like major depositories use heartbeat and voice print for stressor signs, because you can pick up that other sound. And you can even do calculations about percentage error that shows if it's a real person or something copied. So there's some really interesting spaces you can get in here. One thing that's interesting I mentioned in the chat.
I'm just gonna have to interrupt you because we're already into the time for the next speaker. It sounds like you guys want to have a really good, interesting chat. If you hang around to the end, he's going to be in breakout room number 2, and you guys can talk for 20 minutes.
Yeah, cool.
Okay, great. Thank you. Let's give him a round of applause, and then we're going to. And then we're going to move on with, who are we going to move on to? Hugo Flores.
Me. Okay, sound check. Can you folks hear this? Sweet. Okay, yeah, so my name is Hugo, and I'll be talking about deep learning tools for Audacity and how we can use these to help researchers expand the artist's toolkit. This work was done in collaboration with Aldo Aguilar, Ethan Manilo, Dmitry Videnko, and Bryan Pardo. So digital audio workstations, also known as DAWs, are the primary platforms used in recording, editing, mixing, and producing sound art or music. As we know, these come in a variety of shapes and sizes. What makes DAWs such powerful tools are the available signal processing effects in the DAW. For example, I can start with a plain guitar track that sounds like this. Then add some amp simulation, EQ, and pitch shifting to make it come out like this. And then finally sprinkle on top some tape delay and chorus to make it sound like this, nice and underwater. So DAWs allow us to build and shape artistic ideas through the manipulation of sound. And it's worth noting that these effects are modular. And they're often developed by independent developers separate from the DAW. And this modularity is made possible by a couple of different plugin frameworks like VST, audio units, AX. So having easily accessible deep learning models would really enrich the ecosystem of tools for sound artists. Deep models for audio come in a variety of flavors, some of which are of interest to sound artists, like source separation, neural upsample, timbre transfer, and neural upsampling, among others. But what would the workflow look like if I was a sound artist right now and I want to use deep learning to make some sort of sound art? So as I mentioned before, using DSP effects is easy since they're well integrated into the DAW ecosystem. You record your audio in the DAW, process using your effect of choice, and then continue to edit and mix your audio. On the other hand, unfortunately, having access to deep models for audio production often requires you to know how to use a command line interface or manipulate a Jupyter notebook. Neither of these things are easily accessible to most sound artists, meaning that using them can be inconvenient or even an impossible process. So if your deep model only has a command line interface available, this is what a sound artist has to do in order to use your deep learning model as part of their creative work. So they first record audio in the DAW, then they have to export the audio to disk, pull up a terminal, learn how BASH works, read the documentation of the command line interface, try installing and running your command line interface, question their existence and why this isn't working and why this has taken 5 hours out of my day, debug for a little bit, and if they were lucky, it worked and they have successfully processed their audio, time to import it back into the DAW and finally edit and mix. And alternatively, some lucky deep models get their own web UI, but these come with limitations like being able to only process 15 seconds of audio at a time, or having a user upload their audio onto a web server, which involves privacy concerns with some users. So with a web UI, the user-facing interface kind of looks like this. You record audio in the DAW, you export your audio in 15-second chunks because you can only process 15-second chunks at once. And for each of these 15-second chunks, you upload the individual chunk onto the web UI, process using the model, and then download the resulting output audio. Then you concatenate all your 15-second chunks and finally import back into the DAW. And now you get to edit and mix. And just to illustrate and drive the point here are some really popular deep models that work like this. There's DMux, there's Splitter, and DDSP with their super cool web UI. So both of these workflows are really inconvenient and they kind of interrupt the entire production process. So can we do better than these two approaches? So in order to figure that out, we kind of have to think from a developer perspective. What if I am a deep learning practitioner? What would the process look like if I wanted to make a deep learning plugin? So this is sort of like what that pipeline would look like if I were a deep learning practitioner and wanted to make a deep learning plugin. I would start out by doing some Python work, training, debugging my model. Once I'm happy with that, I can serialize and export my model to Torch script or Onyx and be able to load it in a C++ application. Then you start writing the actual plugin, write some DSP code to handle the incoming audio, process it with a deep model and spit it back out. Then you write your GUI code. And finally, once your plugin is ready, you put it up somewhere on the internet and you distribute it. And the thing is, especially if you have been writing Python code for the last 8 years, writing audio DSP programs in C++ can be kind of spooky. Yeah, so the problem ends up being that developing an audio plugin for a DAW can be costly and such a lengthy endeavor. So most deep learning models rarely make it to the hands of end users. And at the very least, you need to know C++, be familiar with a plugin framework like Juice, and have knowledge of some low-level DSP programming techniques. And if you want people to download your plugin, you most likely need to be familiar with some sort of web development to make the website and have people download and promote your plugin. And this has very little overlap to do with the skills needed to make a deep model for audio. To make a deep model for audio, you need to be familiar with Python, have some deep learning knowledge, know how to program using a deep learning framework like PyTorch or TensorFlow, and be familiar with some high-level DSP techniques, which means that your skill set needs to be pretty wide to be able to make a deep learning plugin, making it not really accessible to the majority of deep learning for audio practitioners. So as a result, most models never really make it to the real world. The research cycle is fast, and deploying a deep learning model is kind of a lengthy process. Some models are perennially stuck as paper demos like these with audio examples, meaning that after the paper is published, your model is probably going to remain in some kind of limbo inside some researcher's hard drive, never to really reach the hands of valuable end users for the betterment of humanity. So instead of having you do the ugly work, we propose a framework that removes the ugly, scary parts of making a deep learning for audio plugin. Once you're done serializing your model, you can wrap it using our Python framework for Audacity models. You upload the model to Hugging Face repo, and that's it. You can load your model in Audacity. And so as you can see now, the skill set required to make your own deep learning for audio plugin is significantly more manageable. So from a user-facing perspective, things get way nicer too. Using deep learning as part of your creative process now consists of much, much easier steps. All you need to do is record audio in Audacity, apply the deep learning effect in Audacity, and you're done. Just edit and mix and keep going with your life. So with our framework, Audacity now supports two types of deep learning tools, a deep learning effect and a deep learning analyzer. Both of these tools take any audio track as input. The deep learning effect is able to process the input track with a deep model and produces any number of new audio tracks as output. The deep learning analyzer, on the other hand, is capable of producing a new label track as output, which contains annotations for the input track. You can kind of immediately see some possible applications for those of these effects. You can use the deep learning effect for anything like neural upsampling, timbre transfer, source separation, speech enhancement, among other things. And the deep learning analyzer comes in handy for sound event detection tasks or musical instrument recognition, tagging, etc. So this is what the framework looks like internally. For the deep learning effect, we use any PyTorch model that is able to take an audio waveform as input and produce one or many audio waveforms as output. For the deep learning analyzer, we use any PyTorch model that is able to take an audio waveform as input and produce a set of class probabilities as output. The internal architecture of the model does not matter as long as these sort of input and output constraints are satisfied. On the front end, we provide a simple package manager interface, which lets users install, uninstall, and apply deep learning models contributed by the research community, aka you. On the left of the UI is a list of built-in models, which with controls for installing and uninstalling models. To indicate what data domain these models work with, we add color-coded tags, which should help users find the right model. To explore models that are uploaded to Hugging Face but are not on the built-in list, we provide an external link that facilitates the model exploration process. And finally, if the user wishes to know more about the model, read the original paper, have access to benchmarks, other information, the user can click on the More Info button, which takes them to a README document written by the model contributor. So yeah, let me take you to Audacity and show you a quick demo. Can you see Audacity right now? Sweet. Yeah, so let's listen to a band. So let's open the deep learning effect. We will be using demux for this, separating into drum space, vocals, and other. So anecdotally, from what I have observed by using this a lot, it takes about 1.5 minutes to separate a 4-minute track using this demux, which is not necessarily a small model, but not necessarily a large one either. Just to give you sort of an idea of how fast this performs, because it runs on CPU. So yeah, let's listen to the separated tracks. Some drums. bass, vocals, other, sweet. So that was a demo. So how do you contribute a model to Audacity? So we provide an API for prepping your PyTorch models. The API is super simple. It consists of using one of two base classes for creating Audacity models. You pick a class based on what your model does. So if it's a waveform to waveform processor, you use waveform to waveform. And if it's a labeler, you use waveform to labels. Within those classes, your only job is to override the forward pass and create a metadata file for your model. So, and we provide a pretty detailed documentation for all of the process from preparing, compiling, exporting, and debugging your deep learning models inside of Audacity. This is available on GitHub and will be accessible through a link at the end of the presentation. We also include an example notebook that walks you through the steps needed to export a model trained using the Asteroid source separation library. In this particular example, we compile a conv-TASNet model for speech separation, but Asteroid contains a wide variety of cool different separation models. So we encourage you to go, mess around with the notebook and maybe, get another Asteroid model up there. So once you've compiled and exported your model, the very last step is to upload it to Hugging Face. So it is available for download inside of Audacity. The repo should be pretty simple to make and only contains these 4 files. Because we're still doing alpha tests, the deep learning tools for Audacity are not yet merged into the main build of Audacity, but we expect it to be merged pretty soon. For now, you can download an alpha version of Audacity with deep learning from our lab website. Thank you for listening. Any questions?
Yeah, thanks for that. I see one question that was on the chat, which is, okay, so my model is uploaded to Hugging Face and then your Audacity project uses it. Where is the processing happening? Is that local to your machine or is that on the web?
The processing is happening on your machine. So your machine is downloading the model and running PyTorch in your computer on your CPU locally. There is no CUDA support at the moment, but I think it's possible to do on Linux distributions.
Anyone want to shout out a question or two?
Yeah, this is just super cool. I love this initiative. I guess I'm curious, so a lot of these deep learning models will typically operate on like a segment or chunk of audio. How do you actually handle that in terms of making this seamless, variable length audio to variable length audio?
Yeah, so we leave that up to the model contributor. So the reason you have to use an API to export your model onto Torch script and not just do it yourself is that we add some checks on top of it. Basically, it's just one big test that class is. So it'll make sure it'll run a bunch of different size tensors through the model to make sure that you're sort of outputting the right stuff and taking the right stuff in. So you sort of deal with the variable length input inside of your pre-processing code.
I see. And so then in terms of Hugging Face, is Hugging Face just being used for hosting these large models, or does its API also provide something to this system?
It's just hosting. It's just hosting them.
I see. Okay, cool. That makes sense.
I see there was another question in the chat from Wansu Kim. Is there any way to use the model on the local system directly, I assume, without going up through Hugging Face?
Yes, you could, but you would have to find where the models are stored, depending on the operating system. That's different, and you would have to create, sort of replicate the Hugging Face repo inside of that folder.
Also, I have another question, if there is time.
Yes.
So first of all, thank you so much, Hugo. That was really wonderful job. I really enjoyed that. my question is that for some models, for some deep learning models, like we have two stages, for instance. We have like the neural network stage, like AI stage, and also like post-processing. Sometimes like that uses like some models, like probabilistic models, to post-process. So my question actually is that, is there any way in this model to also, engage those post-processing things? Because some post-processing have like some parameters that need to be tuned. So in here, you only push the bottom and just does the processing and just delivers the audio. So did you have any ideas about like those scenarios that we have like multiple stages?
Yeah, so there's sort of like two answers to this. So if your model, if you have any post-processing code that doesn't require user input, as long as it's written in pure Python and PyTorch, it would work. But if it requires some sort of user input, we don't currently support building like controls dynamically. Like if you wanted a slider, we can't do that yet. But we're open to contribution. Audacity is a big open source project, and I'm sure that there will be people interested in adding sort of this like dynamic building of controls like sliders or text boxes if you wanted to do text to speech, things like that.
Right. Thank you.
Thank you.
We are right on time, so let us move on to our last speaker of the evening, Ethan Manilow. And why don't you tell us about what's going on with source separation with a whole new way of looking at it and doing it.
All right. Yeah, while I'm getting set up here, I'm just gonna like share my screen. But yeah, I just want to like, first of all, thanks everyone for sticking around all the way to the end. It's really nice to see a bunch of like old and new faces, especially like, I know there's people on the East Coast who are up pretty late, so I appreciate that. Yeah, and I also want to thank, all my lab members. I've been really humbled to see all your work in one place, so it's really great to see everything. Yeah, I'm going to play just a little test audio. So if you didn't hear a piano and a violin playing, just yell at me and I'll stop. So this is work that is hot off the presses, was on archive as less than 48 hours ago. I guess I should introduce myself as well. So I'm Ethan Manilow. I'm a final year PhD student. I'm in the lab with all these other great PhD students. And so I'll talk about some fun explorations I've had using pre-trained models for things like source separation and maybe this tenuous example with style transfer. But so first I'll talk about like what actually is source separation. So source separation's got a lot of attention recently, but just kind of the basics of it. When you record a song like in a studio or in a DAW, right? Usually what you want to do is you want to record each of these instruments individually, right? So you want to have your guitar in a separate track, then your keyboard, etc. And what you'll do is you'll usually pay a recording engineer to mix all these things together so that they sound good when you play them over the radio, and that final radio song is kind of the mixture. And so source separation is the opposite process, where we take that song that you hear over the radio and we're going to do some kind of magic, and then we're going to try to split it out into its individual pieces and get some estimate for what these sources sound like individually. And so one of the core challenges for current music separation research is that the data sets that we use are really small. And this is actually one of the machines that I've been raging against for the past few years. So if you look all the way to your left, there's this data set called MuseDB 18, which is kind of the de facto standard data set. And it only has 150 examples in it. To just the right of that, the red bar is the Slack 2100 data set, which I made a few years ago, which is a little bit bigger. But if we compare music separation data sets to their older siblings in the speech separation world with MuseDB or with Wall Street Journal or LibreMix 2, right? These music separation data sets are kind of dwarfed by that. Another big limiting factor that we have in the music world, right, is the types of sources that we're able to support through these data sets. So as I mentioned, this de facto data set MusDB18, right, one of the great things about it is that there's recordings of live musicians, but one of the hard decisions it makes about the world is that there are only 4 sources in it, right? So vocals, drums, bass, and then there's this 4th catch-all source that has every other type of source in the world, saxophones, violins, guitars, didgeridoos, kazoos, zithers. I could go on forever, but if you wanted to separate any of those 2 sources from each other, you can't do that, right? Because this data set doesn't support that. On the other hand, as I mentioned, this data set I made a few years ago, SLAC 2100, right, actually does have a lot of different support for a bunch of different sources, but they're all synthesized, right? So all this data is synthesized, right? And so its ability to generalize to these live recordings of live musicians, right, is kind of questionable. So a core driver of this work is kind of answering how can we get models or somehow access to systems that have had exposure to more data. And by more data, I mean both in terms of raw hours of audio, but also a variety of different source types that are not captured realistically by these other data sets. And to this end, I'm gonna show off the system that I'm calling Tagbox, which is a combination of OpenAI's Jukebox and a music tagger. And if you're familiar with VQGAN+CLIP, it's a very similar concept where we use the music tagger to guide gradient ascent in the embedding space of Jukebox. And so the use cases I'll show off are source separation and a little bit of style transfer, but big asterisk on that. So first, let's dive into music taggers, right? So music tagging has been this core task in music information retrieval. And the idea here is we want to predict a set of semantic labels called tags from the audio content that we hear. And so these tags are things like instruments presence, genres, moods, and stuff like that. And there's been a lot of work actually using convolutional neural networks for this task. But one of the main draws for me for this music tagging task is the data sets, right? So here we have our friendly neighborhood music separation data sets, right? And if you compare the music tagging data sets on the same chart, right, again, we kind of dwarf the source separation data sets. So we have up to 300 times more data than MusDB using these standard music tagging data sets. And so one of the core questions is, where do these tags come from and how can they be useful? So these tags actually come from these old crowdsourcing experiments from 10 years ago. As you can tell by this very, very outdated user interface, it was kind of this CAPTCHA setup where you had to corroborate the tags that someone else gave to a song, right? And kind of one of the catches here is that there's this open vocabulary, right? So you can type anything into this box. So we get a lot of variability in what people actually contribute to these systems. And that's good and bad. On the one hand, there's lots of overlap. So things like, if you want to hear a male singing, right, you get tags like male, male vocal, male voice. But on the other hand, we get a whole lot of rich data about what instruments are available. So depending on the data set and depending how you aggregate these tags, right, you have anywhere between 16 and 14 instrument tags, right? So next, the key question is now we have this audio that's paired with this tag data, right? How can we use this for something like an audio task like source separation and leverage that? And that audio to audio piece comes in the form of OpenAI's Jukebox, so OpenAI's Jukebox is this kind of this large generative model for musical audio. And through the use of a lot of high-powered computers and high-powered lawyers, right, OpenAI was able to train this on 1.2 million songs. And just because I can't help but show this graph one more time, now we have, again, on the left, our very small music separation data sets, and to the, a little bit more to the right in green, our music tagging data sets. And I'm just going to show you just how much bigger this data set from Jukebox is, right? And so there's a whole lot of great audio in here that's just waiting to be exploited. And don't actually take my word for it. Rodrigo Castellón and Chris Donahue, who's on this call, right, actually have this really exciting paper coming up at ISMIR where they show for a lot of downstream classification tasks like beat tracking and coincidentally music tagging, right, they're able to use these representations that Jukebox learns to get really great success and state-of-the-art in a lot of these situations. So let me open up the box, so to speak, and explain how Jukebox works. So At its core, Jukebox has two pieces. The first is a vector quantized variational autoencoder, actually a set of 3 of them, and the second is a language model. And so with our set of VQVAEs, what we're going to do is we're going to take some input audio, and we're in parallel, we're going to send it through 3 different encoders, VQVAE encoders, and these are non-quantized, and they have different rates. So we're compressing the audio at different rates, and then what happens is in those non-quantized continuous spaces, we're going to quantize those and get what we call a series of codes. And those codes are going to be passed to each of these respective decoders, and we're going to train each of these things independently on a reconstruction task. And so the reason we have 3 is we have 3 different compression rates of our audio, right? And one of the other big pieces of Jukebox is these language models where we take in these codes and we predict new codes, similar to the way GPT-3 works or any of these other large language models. But actually, for my situation for Tagbox, we're actually not using that language model at all. And additionally, we're not even using the top 2 layers of the VQVAE. We're only using the bottom VQVAE. And that's because it compresses the audio the least, and therefore we get the highest fidelity, right? So coming back to how all this gets put together, right? We have OpenAI's Jukebox, and we have our music taggers. And so now we're gonna use these taggers, the tags that we get, to guide the location in the embedding space. And so what's really neat about this is we're not actually updating the weights of either of these models. We're just, for each example audio independently, we're gonna update our gradient ascent. And so let me just show you how this works. So if you're familiar with VQGAN+CLIP, this will seem familiar to you, right? So first thing that we're gonna do is we're gonna take a piece of audio, we're gonna put it through our Jukebox encoder, get some location in our embedding space. We're going to decode that Jukebox embedding space back to audio. And then here's the trick, is we're going to take that original input audio, and we're going to use the Jukebox decoded audio to mask the input audio. So effectively, we're asking Jukebox what to remove from our input audio, and that stuff that we were removing and from the input audio, we're going to input into a tagger, right? We're going to get a set of estimated tags, and then we'll predefine a set of tags, and usually that corresponds with some instrument that we want to separate, and we're going to compute some cross entropy loss and then use that to guide our gradient ascent in the embedding space. So we're going to do this for a fixed number of iterations until we're happy with the result. And so I want to talk a little bit about the masking, because that's kind of a crucial component of this, right? So at a high level, masking is this technique where we're going to convert both of our pieces of audio into spectrogram, and we're going to use one to individually remove elements from the mixture that we care about to get our source estimate. And masking is this core component of source separation literature, and a lot of networks in supervised settings actually use the mask, predict the mask directly. So there's a lot of neat things about Tagbox. Is one I already mentioned, is that we're not updating the weights of either of these models, right? And neither of these models are trained at all explicitly for source separation. And because of that, right, we don't need any isolated source data like we would when we train a typical source separation network. So just to see how well this worked, just because we didn't want to just put this out there and believe that it worked, right? We did a set of experiments where we compared Tagbox to a set of state-of-the-art supervised neural networks and some old unsupervised systems. We used the test sets of MuseDB and Slack, and we measured using this measure the performance using this standard source to distortion ratio. So here are the systems we compare against. DMUX, which is state-of-the-art as of maybe a month or two ago, which is a supervised neural network system, and this is trained on the live recordings of the MuseDB dataset. Cerberus, which is another supervised neural network, but now this is trained on the synthetic synthesized data from the Slack 2100 dataset. And then I reached all the way back about 10 years ago to our humble BISH Bash leader Zafar's work and got RepitSim, which is unsupervised. It's not a neural network, it's kind of this hand-designed vocal separation system, and because it's unsupervised, it doesn't need training data. And then just to complete our table here, we have Tagbox, which is the thing I'm presenting. So let's first look at these DMUX results. And so higher values are better for all these numbers. So the bigger the bar is, the better it's doing. And this is the state-of-the-art DMUX. And you'll see on the left here in the gray is the MuseDB test set, and on the right with the maroon background is the Slack test set. And there's there's this huge gap here, right? And so because these systems are supervised, if you don't have source data to train on to do the separation, then you can't actually do the separation. And so there's a similar story here with Cerberus, right? Cerberus was trained on the right data, the synthesized data, and therefore there was no vocals in there, and so there's no vocal data to separate. Another thing I want to mention here really quickly too is that the Cerberus model was trained on the synthesized data, and if you test it on the live recordings, there's this huge distribution shift. Right? The synthesized data sounds very different from the live recordings, right? And so you get this huge performance drop when you go from one distribution to the other distribution. And finally, rounding out our unsupervised baselines, we'll talk about RapidSym, which has this lonely vocal separation because it was hand-tuned for vocals. So now let's see how Tagbox stacks up to all this stuff, right? And so Tagbox, we can now get at least some kind of source separation estimate for every single source that we test, and they're pretty consistent too, right? So there's not any kind of precipitous drop, right? Because we're not doing any training, and therefore there's no distribution, or the training that we are doing happens before we're doing any separation, so we don't have to worry as much about distribution shifts. And I kind of want to just show you all these results all at once, and just point out, just underscore this point that Tagbox is the only system that I'm showing you here that is able to separate all those different source types. And so this is actually super amazing and great. But before we kind of get carried away here, I want to put the brakes on this hype train, and before you throw out your existing purpose-built separation systems, I kind of want to just point out here that there is still a very significant gap between these purpose-built separation systems and Tagbox. And just anecdotally, I don't know if I'll have time to go into it, but there's a few finicky things about what Tagbox is willing to separate. But let me dive into some separation examples. And so here's some examples from the real world, right? And so this is a song that probably everyone is familiar with, maybe not, but this is Wonderwall by Oasis, and I'll play the mixture, and then I'll play the output of trying to optimize these vocal tags. So anyway, here's Wonderwall.
Today is gonna be the day that they're gonna throw it back to you. By now, you should have somehow realized what you gotta do.
And so here's what happens when we just run Tagbox and just tell it to isolate the vocals.
Today is gonna be the day that they're gonna throw it back to you. By now, you should have somehow realized what you gotta do.
Great, so now I have one more example, and this is a piano and violin duet, and this is a theme from Howl's Moving Castle, and here's what the mixture sounds like. And here is just asking Tagbox to isolate the violin tags, or the string tags. Okay, so I know I'm running a little bit over, but I have just one more example and then I'll wrap up. And so this is my, I'm going to say quote unquote style transfer examples. Bryan and I went back and forth about whether or not these are actually style transfer. I will let you decide. So kind of the core of what's happening here is we're doing all the same Tagbox setup, except we're removing this masking step and just letting Jukebox optimize this tag with whatever it wants to do. And in some cases, I haven't noticed in every case, but in some cases, it sounds like it will pluck this guitar. So what you'll hear is the input mixture, and then I'll play, I guess I'll play the input mixture and then I'll describe what you're hearing next.
But all it says to you is don't turn back.
And so to me, what it sounds like is a guitar plucking that melody in the middle of a snowstorm. And so I'll play this for you. So I manually cleaned this up a little bit just so you can hear it a little bit better. Again, this is all tenuous, your mileage may vary, but here's the cleaned up version. Okay, so wrapping up, Tagbox is a system that combines OpenAI's jukebox and a music tagger, and we do gradient ascent in the embedding space of jukebox using the tagger, and I've showcased some really some results for source separation, some less impressive results for style transfer, and so I think there's actually a lot of cool areas for exploration. I'm over time, so chat with me afterwards, and I want to thank Patrick, Prem, and Bryan for helping me with this work. And there's a demo site, the link on screen, and you can follow me on all the socials, etc. Thanks so much.
Well, we actually have maybe time for one question, then we'll do shout outs, and then we'll go to the breakout rooms. And remember that when we do the breakout rooms, the speakers, hey, Ethan, could you stop sharing? And maybe for the speakers, if you wanted to put the links to your where you want to send people into the chat, that might be a good way for them to get at it right now. So anyone got that one key question for the general audience for Ethan?
Okay, I'll take it. Sorry if I got in before somebody, but so I was just wondering, you might have said this, but Ethan, are you you in your diagram you gave an example of where you take the difference between the jukebox output and then just clarification on this, you're using their model and changing. Are you starting with the pre-trained model of theirs and actually changing doing backprop all the way through the VQ model?
Yeah, so the backpropagation originates with the tags that are output by the tagger, right? And then you compare that to some preset define of tags that you care about, right? And then the backprop goes through the music tagger and through the decoder from VQGAE, and then we just move around in that embedding space to produce the output that matches those tags.
Okay, cool. That clarifies something for me. And then the other thing is are you doing separate models for, I think you just answered this, but you're not doing separate models for each tag that you're attempting to target, right? You have a set of tags and you're just taking kind of an argmax of which tag is closest and kind of pushing your model in that direction for each separate tag.
Yeah. So the way these tagging models work is they're multi-instruments, they're like multi-instance or multi-class models. So you can, they're not one hots, they're kind of multi-hots. So you can have the system arbitrary optimize any number of tags. And so if you wanted to do bass and voice at the same time, you could just use the same model.
Great, thank you.